morning, dear students. Welcome back to my spectroscopy class. Let me continue the electronic spectroscopy. That is, last class I have mentioned about the different types of the electronic transition that are possible. The most probable transition are from the zero vibrational level of the ground electronic state to the various vibration level of the higher electronic state. Or next higher electronic state is the most probable vibration, because there is a greater probability that the molecule is to be found in the zero vibration level. Okay, at the ground state, that is equal to zero in the ground state. So there is a great number of molecules there. So most probable transition are always from those transition from nu dash is equal to 0 in the ground state to nu double dash is equal to 0 in the ground state to nu dash is equal to 0, 1, 2, 3, etc. in the excited electronic state, or next second electronic state, like this. That is, nu 2 dash is equal to 0 to nu dash is equal to 0. That is represented by 0, 0 transition, or nu 2 dash is equal to 0 to nu dash is equal to 1. That is represented by 1, 2 transition, or nu 2 dash is equal to 0 to nu dash is equal to 2. That is represented by 1, 0 transition. This is 2, 0 transition. Or that is equal to nu 2 dash is equal to 0 to nu dash is equal to 3. That is called a 3, 0 transition. All these are the main types of the most probable transition that is possible according to the famous principle, that is Frank quantum principle, that is possible in a molecular system by electronic transition, and that is usually represented like this. This is the internuclear distance. Internuclear distance, and this is the potential energy, and this is the internuclear distance r. So this is our Morse curve. This is the ground state. This is the excited state. So transition is from, this is nu 2 dash is equal to 0. And 1, 2, 3, etc. Here nu dash is equal to 0. Nu dash is equal to 2. Nu dash is equal to 3, like this. Here nu 2 dash is equal to 1, 2, 3, etc. Out of this is the most probable transition. Like this. This is 0, 0, or it may be like this. Or it may be like this. All these transitions are represented like this. 0, 0, 1, 0, 2, 0, 1, then 2, the next is 3, like this. So this is a type of transition that is possible, because there is a more probability for the molecules to be found in the zero vibration level in the ground state. And there is also a definite probability, a slight probability for the transition from this side, from the higher vibration level, because the higher vibration level, the molecules seems to be found at the extreme of the potential surface. Extreme you are familiar with this type. Middle, the ground state with the nu dash equal 0, the probability is at the middle, but as the vibration increases, the probability tend to change to the extreme position. So next, I wish to discuss about determination of dissociation energy. Determination of dissociation energy. D0, D0 is represented of a diatomic molecule. Diatomic molecule using the electronic spectra. Electronic spectra ഉപയോഗിച്ചുകൊണ്ട് നമുക്ക് ഒരു ഡയറ്റമിക് മോളിക്കുലർ സിസ്റ്റത്തിന്റെ dissociation energy കണ്ടുപിടിക്കാൻ പറ്റും. Like H2 giving 2H gas, okay, or N2 gas giving 2N gas. So we can find out the dissociation energy D0 of such molecular system. O2 gas giving 2O gas. So the electronic spectroscopy is very helpful in determining the dissociation energy of such a molecular system. For that you have to consider a case in which the excitation energy of the molecule is too large that the higher potential, the upper potentiality curve is shifted to a greater extent on the right side. അങ്ങനെയുള്ള ഒരു പൊട്ടൻഷ്യൽ കർവിനെ കുറിച്ച് നിങ്ങൾ കൺസിഡർ ചെയ്യാം. So consider a potential energy curves in which the upper curve or the first excited state curve is shifted to the right side to a greater extent. അങ്ങനെയുള്ള ഒരു പൊട്ടൻഷ്യൽ എനർജിയെ നമ്മൾ കർവിനെ നിങ്ങൾ കൺസിഡർ ചെയ്യുന്നു. So this is the figure. This is the R potential, that is internuclear distance R, and this is the E potential energy. You consider this a ground state, electronic state. This mosca represents the ground electronic state. Okay. So this is the limiting. Okay. Then ഏകദേശം അതിന്റെ ലിമിറ്റിംഗ് എന്ന് പറയുന്നത് nu d എന്ന് കൊടുക്കുക. But after that, beyond that, the molecule will undergo dissociation. So this is nu double dash. Okay, nu double prime 0, nu double dash 1, nu double dash 2, nu double dash 3, nu double dash 4, etc. Okay. Now you consider the excited state, electronic state, the excited electronic state of the molecule. The situation is such that the molecule possesses extremely large excitation energy that the curve is shifted towards the right. The minimum of the curve is shifted extremely towards right. അങ്ങനെയുള്ള ഒരു curve ഇങ്ങനെ കൺസിഡർ ചെയ്യാം. Okay. So you know the concept. Consider here. So this is the excited state. This is the ground state. The electronic states are, that is nu dash is equal to 0, nu dash is equal to 1. Okay. This is the various vibration level, and this is the limiting level. There is nu d, nu dash d, either nu double dash d. So we have, you consider the excitation of the molecule, the transition. Consider the transition of the molecule, such a transition of the molecule, such that, they would have seen the consider here. Consider this transition. This transition of the molecule from nu is equal to, consider the transition nu dash is equal to 0 to nu d. Nu d transition, nu dash d electron transition consider here. When this transition, electron transition occurs, consider the potential energy curve of the molecule such that the excited state is so much excited that the minimum of the point is shifted to its extremely right. Okay. So that corresponding to the vibration level nu dash d, the molecule undergo dissociation, so it does not come back. After the vibration is so loose that the molecule vibrate to an infinite distance. Nu dash d lekkulla transit ettumbol the molecule is so excited that the vibration of the molecule bring the molecule atom to an infinite distance, so that it does not the molecule does not return. So it will lose the harmonic oscillation. Harmonic oscillation la concept avada nashtaപ്പെടുകയാണ്. So what to remember here, this is the ground state. This is the dissociation energy. I have to remember D0 dash dash, and this is the D0 dash. This is the X, that is the by dissociation energy of the excited state. This is the dissociation energy of the ground state, and I think this is the and this is the excitation energy. Excitation. ഇത്രയും കാര്യങ്ങളൊന്ന് അറിഞ്ഞിരിക്കുക. Excitation. Okay. This is the excitation, and this is the D0 excited, the dissociation in the excited state, and this is the dissociation energy of the molecule in the ground state. Okay. What is dissociation energy? The minimum amount of energy required by a diatom molecule to undergo dissociation into atom from its vibrational from the zero vibration level, the lowest vibration level നിന്നുകൊണ്ട് തന്നെ അതിന് ആറ്റമായി ഡിസോസിയേറ്റ് ആയിട്ടുള്ള ആവശ്യമായ എനർജിയാണ്. The minimum amount of energy required for a molecule to dissociate into atom, in its lowest vibration state. അതാണ് with respect to this ആണ് നമ്മൾ പറയുന്നത്. ഏതെങ്കിലും ഒരു മോളിക്യൂളിന്റെ in a given electron state. So the dissociation energy D0 of a molecule is defined as the minimum amount of the energy required for the dissociation of the molecule into atom in its lowest energy vibration level in a given electron state. So this difference with respect to nu is equal to 0 ആണ്. We have to calculate the dissociation energy up to the surface of the potential surface distance. So a ground electron state, the ground electron state has a D0, that is called the dissociation energy of the ground electron state, that is represented by D0 dash. The D0 dash. That is the difference in the energy between nu dash dash d minus nu dash dash 0. Nu dash 0, that actually represents D0 dash dash. That's the dissociation energy. Dissociation energy of the ground state. രണ്ട് തരത്തിലുള്ള എനർജിയാണ് നിങ്ങൾ മനസ്സിലാക്കേണ്ടത്. ground state. While the dissociation of the excited state, that is nu dash is equal to 0 to nu dash is equal to nu dash d minus nu dash is equal to 0. അതിനെയാണ് that is called d dash 0 is the dissociation energy. Energy of the excited state. So in this figure, the lower D0, that is the difference, energy difference between nu double dash d and nu double dash 0 represent that difference represents dissociation at the ground state, while in the upper curve, that is the difference in the nu dash d and nu dash 0 represent the dissociation energy or the excited state. Evidently, the excited dissociation energy is lower than the ground state dissociation energy. Okay. From this figure, you have to remember that E is the excitation energy. E is the energy in excess of d00. ഇതിൽ നിന്ന് അധികമായി കിട്ടുന്നതാണ് excitation. അതായത് excitation energy contains the dissociation energy of the excited state also. Okay. Excitation energy good ഉണ്ട്. So d00. Again, നമ്മൾ മനസ്സിലാക്കേണ്ടത് consider a transition of the molecule. So above this, that is nu dash d2 nu double dash d2 nu dash d എന്ന് പറയുന്ന ടോട്ടൽ കാണിക്കുന്നത് excitation energy ആണ്, because the energy in excess of the dissociation energy of the ground state is the excitation energy of the molecule. Okay. So suppose you consider the excitation, the electron transition of the molecule from nu double dash 0 to nu dash d. Okay, this consider your excitation electron transition consider. During this electronic transition, what happened is that, so when we consider this electronic transition, that is nu 0 to nu dash d, during this electronic transition, the molecule is excited largely to a large distance, excited largely that the atom that undergo vibration does not come back, it will vibrate to an infinite distance, so that it undergo leading to the dissociation. So this nu d represent the limiting vibration for the dissociation. So it is a nu limit. Limiting vibration. The minimum amount of the vibration that required that dissociate the molecule is called the nu limit. So you have to remember then nu double dash 0 to nu d limit എന്ന് പറയുന്നത്. Okay, that is, this is called the nu limit. So nu bar d limit is equal to, your limit is equal to continuous limit എന്നാണ് അറിയപ്പെടുന്നത്. That is equal to d0 double plus E excitation. Your equation. Okay, good answer. Consider the excitation, the electronic excitation of the molecule from a zero vibration level in the ground state to the nu dash vibration level in the excited state. This vibration always leading to the dissociation of the molecule, because the molecule is excited largely that the atom undergo dissociation, because the vibration is too loose that it move to an infinite distance. So that leading to the dissociation. Therefore, that frequency in the excited state is called the limiting frequency for the dissociation, or continuous limits. Beyond that, there is no vibrational condensation or continuum always we can see after nu dash d, because it will not obey the simple harmonic oscillation rule. The continuous so taking so it is called this is nu dash d correspond to the limit, continuous limit, that is equal to d double dash 0 plus E excitation energy. Okay, this nu dash limit can be measured from electron spectroscopy. In the electronic spectroscopy, that is nu dash 0, nu dash is equal to 0 to nu d, that is called nu d nu, that is nu 0 line. Okay, this can be, the nu limit can be obtained from, measured from the electronic spectroscopy. Electronic spectroscopy നമുക്ക് ഈ വാല്യൂ കിട്ടും. And also the E excitation can be obtained, measured from the atomic spectroscopy. Atomic spectroscopy value. So this value is obtained from the atomic spectroscopy and this value is obtained from the electronic spectroscopy. So knowing these two values, we can determine the ground state dissociation energy of the molecule. So we can find out that determine the ground state dissociation energy of the molecule by measuring nu bar limits from the electron spectroscopy and by measuring E excitation from the atomic spectroscopy. Thus we can determine the ground state dissociation energy. And again you have to remember, nu continuous limit is nu bar like Mariana. Limit is equal to equation that is equal to nu break that is equal to nu bar 0 0. Done. That is equal to that is called a nu bar 0 0 plus d dot 0 0. So this is a represent nu dot 0 0 line and nu dot 0 0 line, and this is nu bar limit. Okay, 0 to nu bar limited. So what nu bar limit is equal to nu bar 0 0 plus d1 0. Okay. Therefore, E equation all these are the centimeter inverse. So alternatively, nu bar limit can be obtained from the electron spectroscopy, and nu 0 0 also obtained from nu 0 0 is also obtained from the vibrational fine structure of the electron spectroscopy. This can be obtained from the nu bar 0 0 can be obtained from the vibrational fine structure of the electron spectroscopy, and nu bar limit can be obtained directly from the electron spectroscopy, and thus we can determine d1 0, the dissociation energy of the excited state. Okay, excited state dissociation energy of the excited state of the molecule can be determined. We can determine both the ground state dissociation energy, and we can also determine the excitation state dissociation energy of the molecule. Okay. This video is equation. This is atomic spectroscopy. This is electronic spectroscopy. Equation nu bar limit nu bar 0 0 plus d1 0. This is electronic spectroscopy. This is vibrational fine structure. Okay, vibrational fine structure of the electron spectroscopy this is electron spectroscopy d1 0 excited state molecule in the dissociation energy. Different types of transition possible in a molecular system. Different types of electronic transition. So we can discuss the different types of electronic transition. We will discuss the different types of electronic transition. Transition in a molecular system. Okay. For a molecular system, there are different types of electron transition. We will discuss here. Depending on the structure of the molecule, okay, a molecule can contain mainly different types of molecular orbital. 3 different types molecular orbital, that is sigma MO molecular orbital, then pi molecular orbital, and a non-bonding molecular orbital, non-n. So, sigma, pi and n. So, 3 molecular orbitals are there in a molecule depending on the structural character of the molecule. Correspond to sigma and pi, there are sigma star and pi star also. Correspond to this, there is sigma star and pi star also. So normally a molecular system contains 5 different types of molecular orbital. That is sigma, pi, n as the 3 bonding molecular orbitals. They are the 3 bonding molecular orbitals, and the corresponding, that is sigma star and pi star, are the 2 anti-bonding molecular orbitals. Thus a molecular orbital system contains 5 MOs, that is 3 bonding MOs, 3 bonding MOs, where usually the electrons in the molecules are filled or entered, and the other are two anti-bonding MOs. Anti-bonding MOs. Okay. So according to molecular orbital theory, the transition that occurs by the absorption of energy from electromagnetic radiation, the transition that the most probable electronic transition that are possible by the absorption of energy from the electromagnetic radiation is that from the highest occupied molecular orbital to that of the lowest unoccupied antibonding molecular orbital. That is the most probable electronic transition in a molecule is that what is between 2 molecular orbitals that lie side by side. That is called a frontier molecular orbital. And frontier molecular orbital theory and so any type of electronic transition in a molecules are always probable that is between any pair of molecular orbitals which lie side by side or which are in close proximity with each other. ഒരു molecular systemത്തിലെ ഇതെപ്പോഴെന്ന് പറയുന്നത്, that is, ഒന്ന് ഒരു ബോണ്ടിങ് മോളിക്കുലർ ഓർബിറ്റലും മറ്റൊന്ന് ഒരു ആന്റി ബോണ്ടിങ് മോളിക്കുലർ ഓർബിറ്റലാണ്. ആ ബോണ്ടിങ് മോളിക്കുലർ ഓർബിറ്റ് ഹൈയസ്റ്റ് ഓക്യുപ്പൈഡ് മോളിക്കുലർ ഓർബിറ്റൽ എന്നും ഹൈയസ്റ്റ് ഓക്യുപ്പൈഡ് മോളിക്കുലർ ഓർബിറ്റൽ ഹോമോ എന്നും അതിന്റെ തൊട്ട് മുകളിൽ കിടക്കുന്ന ആന്റിബോഡിങ്ങിനെ ലോവസ്റ്റ് അൺഓക്യുപ്പൈഡ് മോളിക്കുലർ ഓർബിറ്റൽ എന്നാണ് അറിയപ്പെടുന്നത്. ആൻഡ് ദിസ് ടൈപ്പ് ഓഫ് interaction is called a homo-lumo interaction, or the overlapping between 2 frontier molecular orbitals, that is homo-lumo. That's called a frontier molecular orbital overlapping in an aripidum. Okay. So the electronic transition in a molecular orbital is always taking place from the highest occupied molecular orbital to the next lowest unoccupied molecular orbital. Then you have to think is that in a molecular system, depending on the structure of the molecule, the HOMO may be either of these 3 MOs, bonding molecular below. HOMO may be sigma, pi or n may be the HOMO in a molecule depending on the characteristic structure. While the LUMO may be always either sigma star or pi star. So in a molecular system, we can analyze or we can predict 6 different types of electronic transition are possible due to the homo-lumo interaction. Okay, since there are 5 molecular orbitals are there, and always the transition is from homo to lumo. That is from bonding molecular highest occupied bonding molecular orbital to the next highest unoccupied antibody molecular orbital. Okay, that's called a homo-lumo interaction. We can analyze, we can predict the transition. There are 6 different types of transition possible in a molecule. You consider a case. I have drawn this. This is the energy. Okay, this is the energy level of the molecular system E, and this is the first molecule of the lowest energy, that is sigma. Okay, sigma. Next comes pi. Next comes n. Next comes pi star. Pi star. Okay. Then next comes sigma star. So these are the 5 molecular orbital. The order, always you know that the electron occupy in the body molecular orbitals in the increasing order of their energy. Okay, always sigma is lower energy than, pi is lower energy than, n is lower energy than, pi star is lower energy than sigma star. So the electron occupy normally the molecular orbitals in the increasing order of their energy in the molecular system. The molecular system, the electron occupy the increasing order of their energy, the molecular orbital first. So the electrons are paired in the molecular orbitals in the ground level. So you have to look here. The different types of transitions depending on the structure of the molecule. Depending on the structure of the molecule, this is a HOMO and this is a LUMO. This is called sigma to sigma star transition. This is the sigma. This is the first transition. Okay, this is a possible transition. Sigma to sigma star, that is 1. Okay, 1. That is sigma to sigma star transition. So you take any one pair as the HOMO LUMO. HOMO LUMO. Transition, electronic transition. According to Frontier molecular theory, according to Frontier molecular orbital theory, that electron transition is always between the HOMO and LUMO. The highest occupied MO2, the lowest unoccupied molecular orbital, and HOMO is always a bonding molecular orbital, and LUMO is the nearest unoccupied anti-bonding molecular orbital in the molecular system. So let's consider that then the transition is from sigma to sigma star. If they happen to be HOMO and LUMO, then they are the highest energy. So Sidana is the highest energy. Then next comes sigma to pi star. Okay, this comes the sigma to pi star transition. Sigma to pi star transition. Okay, sigma to pi star. The transition like this, sigma to pi star, this is 2, transition number 2. Okay, sigma to pi star transition, pi star. The next comes n2 sigma star. Okay, sigma to pi sigma to 6, okay. Pi 2 sigma star, pi 2 sigma star transition, pi 2 sigma star transition. Pi 2 sigma, this is transition number 3, pi 2 sigma star transition, and right to pi 2 sigma star. So these are the 3 transition that are higher, the order of the energy sigma to sigma star, sigma to pi star, and pi to sigma star. They are usually of high energy, that their transition usually occur at the far UV region. This 3 transition, okay, this 3 transition usually occurs in the far UV region, because the system has no unsaturated system. Okay, the നമുക്ക് സംഭവിക്കുന്നത് far UV region. So this has no importance in a ordinary molecular system. But the other 3 transition, that is called pi to sigma star, pi to pi star, then n2 sigma star, then pi to pi star, and n2 pi star transition. That of importance in the electron spectroscopy. That is n2 pi star, n2 sigma star, then pi to pi star, and n to pi star transition. N to pi star transition. That is 4, 5, and 6. This transition. Okay, next comes n2 sigma such transition is less energy than, greater energy than. Pi to pi star transition is greater in energy than n to pi star transition. So there are thus we have in a molecular system 6 types of electronic transitions are possible. That is sigma to sigma star, sigma to pi star, pi to pi sigma star, then n to sigma star, and pi to pi star, and n to pi star transition. N to pi star transition, out of which sigma to sigma star, okay, sigma to pi star, and pi to sigma star. The first transition is the sigma to sigma star, then sigma to pi star, and pi to sigma star transition. This takes place in the far UV region. They are highly energetic. While the other 3 transitions, that is n to sigma star, then pi to pi star transition, and n to pi star transition takes place in the near UV and visible region, that is 200 nanometer to 800 nanometer region. These three electronic transitions are important. These 3 electronic transitions are important in the UV visible region. UV visible region എന്ന് പറയുന്ന ഇലക്ട്രോണിക് സ്പെക്ട്രോസ്കോപ്പിയിൽ നടക്കുന്ന പ്രധാനപ്പെട്ട 3 ട്രാൻസിഷൻ ആണ് n to sigma star transition, pi to pi star transition, and n to pi star transition that usually takes place between 200 nanometer to 800 nanometer. So these transitions are important in electronic spectroscopy depending on the molecular structure of the molecule. So any molecular system which contain an atom, heteroatom with the lone pair electron. For any molecular system which contain an heteroatom with the lone pair electron like nitrogen, oxygen, sulfur, etc., or chlorine halogen, they can show the characteristic n to sigma star transition, and we can analyze the structure of the molecule. Similarly, any molecular system which is unsaturated, is purely unsaturated system, that can cause effective and cause pi to pi star transition by the absorption of UV and visible radiation, and thus we can analyze the molecular structure. Similarly, any molecular system which is in conjugation with an heteroatom, and a heteroatom in conjugation with the bond, there is unsaturated system. Suppose a molecular system which is an unsaturated system, okay, but at the same time it contains an heteroatom, that it can again show n to pi star transition, and that also get absorbed in the visible region. Okay, then that we can study the electron spectroscopy. So based on this transition, we get about the information of the structure of the molecular system. That is n to sigma star, pi to pi star, and n to pi star transition that usually takes place between 200 nanometer to 800 nanometer. We can study the molecular structure of the molecule. Depending on the characteristic structure of the molecule, if the molecule contains a heteroatom in the molecular in its like a nitrogen, sulfur, oxygen, chlorine, halogen, etc. So surely it shows n to sigma star transition by the absorption of UV radiation. Okay, thus by the electronic excitation we can get the structural information. Similarly, the system is unsaturated system with the conjugation, double bond or triple bond, that will definitely shows pi to pi star transition that usually happens in the visible region. Okay, that molecular structure can be analyzed using the electron transition. And similarly, a system in which it is double bonded, unsaturated along with an heteroatom, okay, like nitrogen, sulfur, etc. Then in addition to pi to pi star transition, it can again show into pi star transition. Then we get the molecular structure can be inferred from this electronic transition. അപ്പോൾ 6 തരത്തിലുള്ള ഇലക്ട്രോൺസിലെ ലാസ്റ്റ് മൂന്നെണ്ണമാണ് ഇലക്ട്രോണിക് സ്പെക്ട്രോസ്കോപ്പിയിൽ വളരെ പ്രധാനമായി വരുന്ന മോളിക്കുലർ സ്ട്രക്ചർ യു വി ആൻഡ് വിസിബിൾ. കാരണം യു വിസിബിൾ റേഡിയേഷൻ കൊണ്ട് അവയ്ക്ക് നമുക്ക് ആ ഇലക്ട്രോണിക് ട്രാൻസ്ഫർ നടത്തി മോളിക്കുലർ സ്ട്രക്ചർ അനലൈസ് ചെയ്യാൻ പറ്റുന്നു എന്നുള്ളത് മനസ്സിലാക്കാം. Then next is multiplicity, spin multiplicity and spin selection rule കൂടെ പഠിക്കാൻ പോവാണ്. ഇലക്ട്രോണിക് സ്പെക്ട്രോസ്കോപ്പിയിൽ we are actually employing the term called spin multiplicity. Spin multiplicity. Multiplicity. That is, spin multiplicity means it is the summation of the ms. The spin or the individual electron in the molecular system is added so as to get the total spin. So, spin multiplicity is the total or the summation of the electronic spin present in the molecular system. Okay, this ms plus ms1 plus ms2, it is summation of ms1. So depending on whether this s, it is called s and s. The spin multiplicity is usually represented by the term s. S എന്ന ടേമിലാണ് നമ്മൾ ഉപയോഗിക്കുന്നത്. Represented by s. The spin multiplicity is represented by s. That is sigma ms. It is the sum of the electron spin present, all the electron spin present in the molecular system. And depending on, there are three types of spin multiplicity. One is singlet, two doublet, and three triplet. So there are three types of spin multiplicity arise, S states arise. Okay, that is usually the multiplicity is represented by means of 2s plus 1 enriched term. The spin multiplicity is usually represented by 2s plus 1, where s is equal to sigma ms. S is called as sigma ms. So there are three different types of spin multiplicity. So what is spin multiplicity? The term 2s plus 1 is called spin multiplicity of a molecular system, where s is the resultant total spin of the electron present in the system, that is equal to sigma ms. It is the vectorial sum of the various spin of the electron present in the molecular system. Depending on the spin multiplicity 2s plus 1, there are three multiplicities: singlet, doublet, and triplet. The singlet means if s is half. Okay, if in a molecular system there is only one unpaired electron, in a molecular system if there is only one unpaired electron, so that s is equal to half, then we have 2 into half plus 1, that is equal to 1, that is called a singlet. It is called a singlet. That is a singlet. So any molecular system which contain one unpaired electron with the resultant s is equal to half is called a single state. എല്ലാ റാഡിക്കളും ആറ്റങ്ങളും ഒരു ഇലക്ട്രോണുള്ള ആറ്റങ്ങളെല്ലാം അല്ലെങ്കിൽ എല്ലാ റാഡിക്കൽ സിസ്റ്റവും വരുന്നതെല്ലാം സിംഗിളറ്റ് ആണ്. Similarly, doublet system, any molecular system in which half 2 into singlet, 2 into half plus 1, that is So any molecular system, any molecular system in which the resultant spin s is equal to 0, resultant spin of the molecular system s is equal to 0, then the multiplicity now become 2 into 0 plus 1. 2 into 0 plus 1, that is equal to 1. That is equal to 1. That is called a singlet. So, the spin multiplicity in which the resultant spin of the electron in the molecular system is equal to 0, that lead to 2s plus 1 as 1, that is called a singular state. Then the doublet state. Any molecular system in which it has s is equal to half. S is equal to half. Resultant spin half, and we have 2 into half plus 1, that is equal to 2, that is called a doublet. So atom species containing single electron, heteroatom containing single electron, and any radical system are doublet, because the resultant spin is half, so that multiplicity is 2. While any molecular system in which the resultant spin is 1. That is the case of diradical. That is a molecular system which contains 2 unpaired electron. 2 unpaired electrons, so that S is equal to 1. S is equal to 1. Diradical ആണ് വരുന്നത്. That is 2 into 1 plus 1. That is called a triplet. അതിനെയാണ് triplet state എന്ന് അറിയപ്പെടുന്നത്. Generally you have to remember this is always നോക്കൂ ഇതിനകത്ത് സ്പെഷ്യൽ കേസ് ഉണ്ട്. The single state in which both the electron are paired in the given molecular level. That is called S0 എന്ന് കൂടെ അറിയപ്പെടുക. So a single state has one special state, that is this state. This state is called S0, that is called a ground state. Okay. So the single state has always an S0 state, that is the ground state, in which the electrons are paired in the same molecular state, that's the ground state. In all other cases, S1, S2, S3 with the electron are antiparallel in the different molecular system are called excited state. Then excited state. So the single state are one ground state, that S0 is the one ground state, while all other are excited state, S1, S2, S3, etc. Similarly, the double state is also an excited state, but normally it is not there. The next is the triple state, which is also an excited state. So you have to remember